I came to NREL in 2008, and it was clear when I got to NREL that the 2010s turned into the decade of wind and solar, and the decade of the 2020s is going to be the decade of hydrogen. The Hydrogen Council is one of the biggest pieces in this. They say 300 billion in the project pipeline in one of the taglines to the left here, but this was from June. 3 months later, it was $500 billion. Those numbers are going up like crazy. They have these different analyses, and Jim alluded to it, things about how much of the energy, so anywhere from kind of 13 to 18% of total energy, global energy potentially going through hydrogen by 2050. And then there's you can look at what's happening money-wise, both in industry, people raising money for hydrogen, and then in governments and government programs to chase hydrogen. And really, the race for hydrogen is on, and it's a global race. I started to do my thesis work in fuel cells in 1994, and it was always that hydrogen was 5 or 10 years away, and that was true until 5 or 10 years ago. And I'll talk a little bit about why that is. But I want to give you, so you'll see things that had never happened before, things within, government, the president pushing things, the Secretary of Energy pushing things. One of these things in particular is this hydrogen energy Earthshot. And it's basically, the tagline is 111. It's to get to $1 for a kilogram of hydrogen in 1 decade. There's lots of graphics and other things, but it's really a driver for this. If we can get down to $1 per kilogram of hydrogen in a decade, it will really help enable a sustainable energy future for the planet that's much more economic than what we would otherwise be able to do. So within some of the recent legislation, so there's this bipartisan infrastructure law. It's being called bill within the hydrogen community, and it has $9.5 billion for clean hydrogen over the next 5 years. 8 billion of that is for clean hydrogen hubs. Jim talked a little bit about this. I expect there to be different regional hubs, and that they'll probably cover the entire country. The language in the law basically says that there's going to be at least 4. I would expect probably 8 or something like that, and the regions to be pretty diverse. But then there's also another 1 billion just for electrolysis research, demonstration, and deployment, development and demonstration, and then $500 million for clean hydrogen technology, manufacturing, and recycling R&D. Compare this to what the hydrogen office has been in the last few years, which is anywhere from 100 to 200 million per year. And it's more than an order of magnitude increase, closer to a factor of 20 increase in terms of what the interest is going to be. And there's a lot of needs to have academics and industry pull some of these things along. So Jim already showed the hydrogen at scale chart. I helped put this together to basically show how hydrogen fits in the energy system. It can be a clean parallel to the grid, the electricity grid, and the natural gas infrastructure. And the more important thing is it can take things that are on the left side, like the renewables, and bring them into the things that are harder to electrify and to decarbonize, like transportation and like industry. Hydrogen can also be used for electricity generation and for heat, and in some cases the high temperature heat or the high quality heat is a real value that hydrogen can bring. But the real benefit of this is the ability to move energy across sector and across time. And then hydrogen also has this unique, clean and efficient end use capability. So those are the key attributes of it. This results in some economic benefits, some security benefits in terms of the energy and manufacturing bases, and then even some economic benefits in terms of jobs, as well as the environmental benefits, which are clearly obvious. But to me, the overarching part of this is that a lot of solutions to these problems can take on one part of this. But with hydrogen and bringing in, especially green hydrogen into these situations, although blue hydrogen is a great stepping stone on the way there, getting all of these benefits in a single energy system really provides a lot of the extra value, making the sum greater than all of the parts. So what the Department of Energy is doing is that they have this broad mission for hydrogen at scale. And it really comes down to how do we make, move, store, and use hydrogen more cost effectively. And there's a bunch of early stage research that's basically helping de-risk these technologies. Cost-effective electrolysis holds a specific place. There's different work that we've done, both experimentally and analysis, that talks about kind of bringing the cost of hydrogen production around how you'd move and store the hydrogen most cost effectively, and then the different areas where you'd actually use this hydrogen and what markets would demand it first, and then what markets it would spill into later based on cost advantages and other considerations. Coming back to this bubble chart, you know, while hydrogen at scale is making, storing, moving, and using hydrogen, making hydrogen is the inherently obvious first step that can spur everything. And a lot of the focus of what I'm working on now is really this electrolysis. And when you think about hydrogen production, electrolysis is really competitive economics, but it also serves to balance renewables in a way that has a larger benefit than just providing hydrogen to these areas. It also allows for greater renewable penetration and enables the whole energy system in ways that go beyond that. But the time frame short and competition is intense. And a lot of what we're trying to do in the Department of Energy and at the national labs is have this coordinated effort that we think is going to be critical. So within green hydrogen or clean hydrogen, you can kind of see with some of these simplified bar charts where we sit today. You know, basically, if you look at this $5 per kilogram number for 2020, you know, the electricity is too expensive just by itself to make this system work. And that's because it's based on current electricity prices and isn't taking into account what will happen with the introduction of more low-cost renewables and what happens in terms of the curtailment options in helping to decrease those prices or offsetting the curtailment issues to basically provide value where you'd otherwise have no value. And then there's this issue of capital costs and fixed O&M that also have to be addressed. We have different pathways. I'll show a couple of them coming up. There's work being done in polymer electrolyte membrane systems, solid oxide electrolysis systems, and now we're looking at alkaline electrolysis systems as well. But we need low-cost electricity. We want to have efficient systems. They need to be low capital cost. We need to work on durability and lifetime, particularly under intermittent or variable operation, because most electrolyzers have been made to run 24/7, which tends to be much easier on the systems. And they've also been over-engineered because they've been using expensive electricity. So saving a few hundred millivolts or tens of millivolts even when you're using expensive electricity allows you to put more into the capital cost of these systems. And so these are all things that we're taking on at some level. There's different pros and cons for each of these electrolysis systems. Alkaline is the big deployed systems. They've been put out in 100 megawatts. There's a project in Saudi Arabia that's coming online that's going to be 2 gigawatts using ThyssenKrupp supplied alkaline electrolyzers. The problem is they have a corrosive electrolyte. They have trouble with differential pressures and they don't really cycle on and off very well. So if you have 24/7 provided input power like at dams, which is where these have usually been sited in large sizes to date, you're absolutely fine and you can do things reasonably cheaply. But the PEM membrane, the polymer electrolyte membrane technology is related to the fuel cell vehicle polymer electrolyte technology. And so it allows for things like differential pressure, better load following and startup and shutdown. But it does have these limitations that the acidic environment requires it use things like titanium, iridium, and platinum, and perfluorinated polymers that are more expensive. So there's a bunch of work that's being done to advance that. Solid oxide systems are more efficient than the alkaline or the polymer electrolyte systems, but they have challenges with the high temperature and thermal integration aspects, and then steam conversion efficiencies. So there's all these different areas. Each one of them likely plays a role in the future. How big of a slice of a pie each one of them has kind of depends on other specific aspects of how they fit into the energy system. So we have, I'm the director of H2New, and H2New is this $50 million over 5-year program. And this is really the basis for the $1 billion over the next 5 years that's coming. So we're expanding significantly. H2New to date has really been focused just on the national labs, kind of doing the base work to put things together. But bringing in industry and academics is going to happen. It was going to happen anyway. And now that we have this new infrastructure language in the law, it's going to explode in terms of who's doing what and how it goes forward. I'm going to not talk about these in the depth that they probably deserve, but basically there's a stack capital cost for PEM electrolyzers that we're trying to take on within H2New. And basically, if we project some things, we can come up with something like a $350 a kilowatt number for these, and we can break those costs up into the different components, and you can see the colors associated with it there. And then basically, we're focusing on these 3 areas that are kind of highlighted to the right: increased efficiency or current density, decreased platinum group metal loading, and scale up. And you can see by these green bars how much we're looking to take out of the cost of these systems from here to kind of 2023, and then the ultimate target of H2New, which would be 2025, trying to get down to $100 per kilowatt by taking out these different areas and having specific targets. And so that's what we're focusing on going forward. Stack costs are one thing, but what you really care about is what the hydrogen levelized cost is. And so what we're looking at here is basically, we can do these things, but what does that mean for the cost of hydrogen? And currently, if you had these systems at the scale that we project to, you might say you could make hydrogen, assuming you had 3 cents a kilowatt hour electricity available 90% of the time, for things like $3.50 a kilogram. We have this target of what we would do going towards 2025 to get towards $2 a kilogram, and then an ultimate target, which is the hydrogen shot type of target for 2030, of how you might be able to even get the costs down to less than $1 per kilogram for hydrogen. So these are the things that we're trying to do on the production side. And a lot of what we're doing in H2New is based on the fact that currently you run electrolyzers at continuous levels, and maybe you'll turn them off. But if you look at kind of those operating modes compared to some of the things that Jim showed earlier, which were like these solar profiles, what that would mean in terms of different operating strategies, and also what this means as far as the engineering of the systems themselves. So existing systems use a lot of platinum, and they have really thick membranes, and they've been over-engineered for durability, and they've been used for things like life support or industrial hydrogen, where the industrial hydrogen is a very valuable commodity where people are willing to pay something more like $20 a kilogram instead of these $2 a kilogram targets. In the future, you basically have to take all of the cost out and figure out how to enable these low-cost electrons to be used. So you want to go to higher operating currents. You're going to use thinner membranes with lower loading. And most of what we're doing is we're trying to focus on what these systems of the future will look like and what it means to try to operate them under the conditions that we think are going to be relevant operating conditions in the future. I'm going to show something quickly here. Basically, this is data from 2017 that talks about locational marginal pricing of electricity this is the Palo Verde area, so it's basically connected to California and Arizona. And this is an area that has about 10% solar and 10% wind in it. And if you look at these locational marginal heat maps to the left, what you can see is when electricity is expensive and when it's cheap. The top one basically is the 25% of the cheapest electricity, and that has a price ceiling of 0.21 cents per kilowatt hour on a wholesale basis. But the average price of electricity, if you took that 25%, is 1.2 cents a kilowatt hour. This is how you get towards cheap electricity. And this is happening just with 20% renewable penetration. As you go down that, you see that you end up with these gaps of expensive times that are early in the morning and late at night and somewhat seasonal when air conditioning loads are still high, but solar fluxes and perhaps wind aren't filling in the gaps as much. And on the right, this gives us an idea of how you might want to operate electrolyzers if you only wanted to run them at the hours where they were the cheapest. And so we're trying to get this information because we recognize that increasing renewables is going to end up with more volatility in these electric markets and create more low value electrons. And how do we basically use that to enable things like electrolysis to bring hydrogen in large scales? These are basically the cost curves per year. And the Palo Verde is this light brown number that was used in the data beforehand. And you can see that there's two other areas that have lower electricity costs available around the year at large amounts of time. And you can take that data and we can do other analysis like this on the right to talk about how we use that, how we'd operate an electrolysis system, and how we get to cheaper electrolysis prices that will enable us to get to the $2 a kilogram or $1.50 a kilogram in this case of produced hydrogen, not using electricity rates that are available in the future, but actually using electricity rates that existed here 5 years ago in the wholesale markets in specific areas. So the last thing I'm just going to mention, because we're interested in interacting with industry and academics more, is what we're doing in H2New, and this is the big consortium that I'm director of. And we're really looking at how do we take on durability. We think durability is a really big issue. And we're looking at fundamental degradation mechanisms, accelerated stress tests, and mitigation approaches. And all of this is really to determine the cost, performance, and durability trade-offs of electrolysis systems so they can be put into the energy system and operate in the most economic way. We're worried about performance, and then we're trying to help scale up. So these are all things that NREL is trying to help lead with a bunch of other national labs, bringing in industry and academics to further move forward. Here's one slide on H2New that has way too much information, and it's basically just talking about the approach that we're trying to take on to basically address these systems. I don't even want to talk about it because I'd rather have discussion and questions, but there's whole presentations that I give just on this. There's a whole bunch of people in H2New who I owe special thanks to for this. And then there's the people who helped in putting the big idea together, which became hydrogen at scale. But with that, I'd be just happy to take any questions that you might have on the topic of hydrogen.